Hello, my name is Nicholas Scarrett, and this is my Physics Lab 4. The purpose of this lab is to compare and contrast the visual model on Tracker versus a computational model on GlowScript of a spring with an attached mass oscillating on the XY plane. Our findings will tell us if the energy principle is satisfied, and the results will show that it is in fact satisfied. So here's some fundamental principles for this lab. Of course, we're going to be using Newton's second law and the energy principle. Newton's second law is going to be very important for the calculation loop, and we're going to be finding the net forces of F spring plus Fg, and the energy principle, which states energy is neither created nor destroyed. The change in total energy in the system is equivalent to the sum of the work done by the surroundings in the energy exchange due to the difference in temperature. And here's some other equations. We of course have the position update, the gravitational potential, the spring potential, and kinetic energy. And quick side note, the system is the mass, the spring, and Earth, and our surroundings are nothing for the context of this experiment. And here are some values we got from the tracker. Here's the actual video and the subsequent graphs it produced in the X and Y. So here are some values we're going to be finding for GlowScript, and I found the oscillation period by plugging this equation, rearranging some things, and we found that the average time is 1.519 seconds, the stiffness is 6.8 to that, and then our relaxed length was found with that stiffness. Now for the code, we start with the mass, the position, and velocity of the system, and then we find, of course, we found the spring force and the relaxed length previously. We plugged in those values, and then down here we used our other formulas that we mentioned to solve for energy, such as energy in gravity and then energy in the spring force. And then now we get into our calculation loop where we have, of course, the net force, which is the added F grav and F springs. And then after that, once we find the net force, we can of course update the velocity and then the position. And then down here, we're finding the deltas and the change of the energies. Okay, now we can see this code in action, and we can see that they're actually deviating quite fast. And so I guess we could explain this with the fact that, of course, there could have been misplacements with the selecting of the center mass. But we know that our system is not actually inside a vacuum. It has to have surroundings that we're not accounting for. And that can explain the difference between these two. And as mentioned previously, there could have been misplacements of the point, the center mass. Rounding numbers could always throw off values, and there was unaccounted surroundings affecting our system. So for the what does it mean, it says for your system is the energy principle satisfied. Well, we can see from our graph that we got from our GlowScript code that there is plenty of energies coming in and out, the gravity and the spring force, but we can see this orange line, it's like a plateau, and the zero is the change in energy, and we see that energy is not being created nor destroyed, meaning that this does in fact support the energy principle. And what does it mean? So using the data you obtain in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X period, and second, by estimating the period of oscillation from the Y period. So I can do this similarly to how I found stiffness, and I actually found stiffness with the Y component, but now I'll be finding and averaging out 5 different periods of time where the graph spiked from its highest to its lowest, up to its highest again. And using this equation, 4 pi squared multiplied the mass of the object divided by the time average time between these two. And we can see that since the periods are different for the X and Y, it's going to be producing different stiffness values as well. Alright, thank you so much for watching.